maybe we will start our next talk. The second talk is given by Professor Shang-Ping from UCSD. His title is El Nino, Indian Ocean capacitor, and Meiyu variability. Right? Okay, let's welcome.
Okay. Yeah, thank you, and I appreciate the opportunity to speak here to a very general audience. We will see how it's going to do. El Nino, of course, is now a household name of importance climate phenomena. And Meiyu, I guess, at least for those that live in China or lived in China, Meiyu is very important phenomenon referring to this southwest, northeast slanted rain band that frequents eastern China along the Yangtze River. Very slight variations in this rain band could lead to heavy rainfall droughts. I guess this summer, I guess the Yangtze River basin has been very hot, as I understand. There are other years that the Yangtze River has experienced historic flooding events. So in that sense, maybe variability is perhaps the single most important climate phenomenon for East Asian countries, from China, Korea, and Japan. So today, of course, people wanted to predict maybe variability for a very long time. And it turns out to be a very tough problem. And today I want to report some of the progresses we have made, meaning the broader community, not necessarily myself. Right? So that is the purpose. And you will see at the end, you might see some AI stuff because I guess the previous speaker talked about AI application. Yeah, so El Nino, of course, is widely known at this point. I guess El Nino became a phenomenon of high interest only around the year 1997, because the second half of 1997 saw one of the strongest El Nino events on record. So El Nino basically refers to the anomalous warming of the tropical or equatorial Pacific. So here I'm showing the sea surface temperature anomalies. Anomalies refer to departures from long-term average climatology and the surface winds. So clearly, El Nino is a basin scale, right? It's stretching from international dateline all the way to the west coast of South America. And then when El Nino happens, it pulls the deep atmospheric convection that produces heavy rainfall. From usually the deep convection is confined in the western half of the Pacific Ocean. But when El Nino happens, you have a high ocean surface temperature, and then the high temperature allows more water vapor, and water vapor together with the temperature are represent the energy of air particles, right? If you have a high energy air particles, it rises to high altitude, and in the process, you would the air particle cooling would cause water vapor inside condense out, and the condensation releases a huge amount of heat to drive the atmospheric circulation. So, so there is a clear kind of effect of the equatorial Pacific warming that's driving this is increased rainfall in the eastern, much of the equatorial Pacific, and then on the Peruvian coast somewhere here, right? So Pacific coast of Peru is one of the driest places on Earth. So that's why you see sand dunes. But during this major El Nino, the sand dunes will transform into Great Lakes. And the lakes lasted for more than a year, right? So this is a tremendous transformation of landscape, making desert extremely wet, making extremely wet place like Indonesia. Indonesia is a place, one of the rainiest place on Earth, whereas during El Nino, because warm temperature drives convection away from Indonesia, Indonesia becomes dry and wildfires enrage this region that usually associated with rainforest, thunderstorms. So this is just give you some of the highlights what El Nino could do, right? And these are just two examples on the western side, eastern side of the tropical Pacific. And then people have kind of mapped out the rainfall changes, right, during an El Nino year. So like in the equatorial Pacific, you see anomalous wet conditions, and then wet conditions across the west coast of South America, including Peru. And then the dry, usually wet region of Indonesia becomes extremely dry, and so on. And also, this is where I'm living and working. So San Diego is here, right? So during El Nino winter, we tend to see more storms, Pacific storm coming our way, increasing the rainfall amounts and so on. But one thing you might, especially for people, for this audience, right? You just was kind of really striking that there's not much anomalies, climatic anomalies being identified in the East Asia region, right? Is that because lack of climatic anomalies or lack of studies, right? So that is something we will see. So this is what I highlight, right? So here's nothing marked here. And El Nino, so this is an index that people use to track El Nino. So sea surface temperature, SST refers to sea surface temperature, right? Surface temperature of the ocean. And Nino 3.4 refers to a region in the central eastern equatorial. In other words, when El Nino happens, sea surface temperature in the Pacific become anomalously high, so that's 0 and plus 2 degrees Celsius. So and you see there are a bunch of El Nino events, and then the cooling events is what people call La Nina events, right? El Nino refers to warming events. La Nina refers to cooling events. And then if you look at the sea surface temperature, El Nino tends to peak in the month 12 months, really refers to December, right? So El Nino peaks in December, decays very rapidly in the following spring, dissipates by next summer. So you might think, El Nino, maybe the people have not marked this region as influenced by El Nino because the summer is the rainy season for much of the so-called East Asian monsoon region. Right? Summer is here, so El Nino has not kind of by summer has dissipated. Maybe that's because the dissipation of El Nino didn't make the East Asia region stand out as other parts of the world. But it turns out that what I just said is false. So it's it's a lack of study rather than lack of anomalies. you will see there's some mysteries on the way. Some of the mysteries solved. I'm very happy to do that. Yeah, anyway, so I said that 1997 is a year of extreme El Nino, right? So look at what happened in the following summer, right? 1998. So some of you might be old enough to remember 1998 summer was extreme flooding, saw extreme flooding along the Yangtze River. Here, it just villages flooded and so on. So extremely dangerous. And people had to camp out on the dike in order to protect the flooding water from intruding their cities, their villages. Anyway, so this is 1998. So this is post El Nino summer, right? Because El Nino peaks in December 1997. And then another example is this. So 2016. So in Wuhan, people observed the record weekly rainfall, 560 millimeters within a week. So this rainfall amount would be probably the annual rainfall Beijing would receive. So all fall within a week. That no wonder, another major flooding was observed in the Yangtze River. So maybe when you just see 2016, it might not ring a bell. But 2016 also happens to be a summer that followed major El Nino. So in December 2015, there was another major El Nino observed. So with these two examples, you might get a sense, right? So something kind of a very kind of a major summer Meiyu. So this will be under the rain band I showed on open slide. So there's a Meiyu tends to produce excessive rainfall somehow in the summer following major El Nino. So this is what I want to convey. Okay, so that's kind of just rainfall, cumulative rainfall. But let's take a look at typhoons, right? So like the tropical cyclones, hurricanes in the Western Hemisphere. So 2016, Wuhan measured record rainfall. In Taiwan, there was the first typhoon of the Western Pacific. Made a landfall in Taiwan on July 8th, 2016. So this is a very late occurrence of typhoon number one, right? Typhoon number one usually happens spring, if not in late winter. But this Western Pacific typhoon number one was observed sometime around early July. And then that made a landfall on Taiwan and causing certain damages. And just as a reference for comparison, right? So in the year before, so by the time July 8th and July 9th, there was already typhoon number 10 made the landfall in Taiwan. So you can see how much delayed, right? The typhoon formation, typhoon activity was extremely weak in the summer following El Nino. Again, right? So something is somehow the East Asia summer knows there was El Nino happening. Yeah. Anyway, so this is more like a systematic analysis of typhoon occurrence, right, over the East Asia. Taiwan is here and Okinawa is here, and this is East China Sea. So this is if you do a systematic analysis of historical data, you will indeed able to identify suppressed typhoon activity in the summer following El Nino. So these are just some examples, right? So somehow from China all the way to Japan, the atmosphere knows there was an El Nino 6 months early, right? Yeah, so if you go to do a systematic analysis of rainfall over eastern China, right? In this case, we use so-called empirical orthogonal function analysis. Sometimes people also call principal component analysis, right? So this is to identify a spatial pattern and temporal time series of how this pattern varies in time. So this mode for July, right, the leading pattern, indeed captures excessive rainfall in the middle and the lower reach of Yangtze River. And then the associated low level or maybe surface wind circulation represents a clockwise rotation. So clockwise rotation in meteorology called anticyclonic circulation because it's against the rotation of the Earth in the northern hemisphere, right? So when you see cyclonic, it just means you are rotating in the same sense as the Earth in the northern hemisphere. And this is anticyclonic. It has anomalous, just means, on average, the circulation here needs to vanish. But anomalous just means when this rainfall pattern happens, you are going to see circulation anomalies in a clockwise sense and maybe anticyclonic sense. And at the center, I'm not going to explain why, but at the center, you expect to measure anomalously high atmospheric pressure at the center of this circulation pattern. So anyway, in other words, when the rainfall along the Yangtze River becomes excessive, you tend to see this anomalous anticyclonic circulation. So, sometimes people call it AAC, right? Anomalous anticyclonic circulation. So this also makes sense, right? Because the southwesterly flow. So in meteorology, when I say southwesterly, it means the winds are coming from the southwest, not the direction that the winds are heading. Right? So the southwesterly wind anomalies transporting moist-laden air from Indian Ocean and the South China Sea and converging onto Yangtze River. So that because the moisture is being transported in the northeast direction, and then if you have convergence, then that means you're losing the water vapor in the air. So the water vapor in the air basically is being condensed in terms of raindrops fall on the ground. So this is consistent, right? So the southwesterly flow carries the high moisture from the Indian Ocean, South China Sea, dump the water vapor along the Yangtze River. So that is consistent with our examples. Yangtze River flooding tends to occur in the summer following El Nino. So when you correlate the time series of principal component of this rainfall pattern with El Nino, you find this pattern is not correlated with El Nino at this moment. Right? Concurrent El Nino is not correlated with this pattern. Instead, El Nino 6 months earlier is highly correlated with this pattern. So this is saying what we are saying here is a post El Nino anomaly pattern. So somehow, again, the East Asia atmosphere system knows there was El Nino 6 months earlier. So this is a little bit strange, right? Just because atmospheric heat capacity is equivalent to 2.5 meters of water. So the ocean has 4,000 meters depth, right? So in that sense, the atmospheric heat capacity is negligible compared to the ocean heat capacity. In other words, for climate variations or climate change, it's actually the ocean that sets the rhythm or the pace of climate variations change. It's because the huge heat capacity of thermal inertia. So in other words, if you see recurrent anomalies over several months, right? So the atmosphere just cannot have this kind of a memory, knowing anything. There was El Nino 6 months earlier. So there must be some oceanic memory mechanism. Remember, there was El Nino 6 months earlier. So that's the key. So in other words, atmosphere by itself cannot have this recurrent pattern that tend to occur in the post-El Nino summer. So that has been the mystery of all these anomalies observed along the Yangtze River or typhoon activity. So people know there seems to be some evidence that East Asia seem to observe post-El Nino anomalies, but what sustains these anomalies has been largely mysterious. This is slow. Okay, yeah, okay. So that's UF analysis, empirical orthogonal function analysis of rainfall over a small region in the eastern China, right? If we do the same analysis over a much larger region from the Indian Ocean to the Western Pacific, the first mode explaining 28% of total variance is correlated with sea surface temperature anomalies in eastern Pacific. This is a concurrent El Nino effect, right? When El Nino happens, this is the rainfall anomaly pattern people expect. For example, the decreased rainfall over Indonesia causing wildfires, right? So that has been heavily studied. We're not going to spend a lot of time on it. So what we want to focus on is this anomalous anticyclonic circulation. So this clockwise circulation pattern. And this color is not optimal, but here actually there's some green color that indicates excessive rainfall. Actually, but the circulation probably gives away the Yangtze River flooding pattern. So this pattern explains 15% of the total variance. And then when you correlate the principal component of mode 1, you are highly correlated with the concurrent El Nino, right? But if you correlate the second mode with El Nino, you find that you are not significantly correlated with concurrent El Nino conditions, but instead you are highly correlated with El Nino 6 months earlier, right? So this has been the mystery. Why the second mode wants to appear, right? When El Nino has died. There's no El Nino to point to in the summer. And people have been looking for answers in the ocean conditions over the Pacific. The color here seems to suggest that there are some anomalies, but these anomalies are not statistically significant. And then in the Western, some people look for Western Pacific sea surface temperature. The color here is sea surface temperature. Surface wind is the same as the left hand. So you kind of see this anticyclonic circulation, but you don't see a systematic, consistent, robust oceanic anomalies. So that has been a mystery. So you might have noticed I hid Indian Ocean under the wrap, right? So you might have thought maybe the trick is there. no surprise. So consistent, robust sea surface temperature, ocean temperature anomalies are indeed found in Indian Ocean. And if you go to correlate the principal component 2 with Indian Ocean sea surface temperature anomalies, the correlation amounts to 0.84, so extremely highly correlated. So it turns out the missing ocean memory was the Indian Ocean, not the Pacific itself. This has been a debate among various people, but I think at this point, the Indian Ocean as the mechanism, as the memory mechanism, sustained the post-El Nino effects that have been observed in the East Asia region. It's pretty well accepted. Yeah. So anyway, so the mystery has been, El Nino peaks in northern winter, right? December decays by the summer, but then there's yellow bars indicate in the Western Pacific systematic anomalies remaining even well after El Nino has dissipated. It turns out it was Indian Ocean surface temperature. So the Indian Ocean grows warmer when El Nino peaks, and the Indian Ocean warming kind of peaks after El Nino and persists through much of the northern hemisphere summer. So that, in other words, this is a really conceptual model, right? So El Nino is like a big battery. So if you put the El Nino battery on, then everything needs to follow El Nino, right? El Nino, after El Nino dissipated, you remove the battery, and the Indian Ocean is capacitor. It remains warm for a while, and then it's going to discharge to affect the circulation anomalies, rainfall anomalies, and then typhoons in the Western Pacific, and so on. So this is we call Indian Ocean capacitor effect. So maybe, I guess, you probably are familiar with El Nino, you're familiar with Meiyu, but you are not familiar, probably never heard Indian Ocean capacitor. Indian Ocean capacitor is the memory bridging the previous El Nino with the summer conditions. So the mystery, in a sense, has been solved. Yeah, indeed, if you go to use global climate model, right, and with the proper initial conditions, you can simulate, you can predict, actually observe the post-El Nino summer anomalies. In this case, we picked three major ones. So after 1983 is the one following 1982 El Nino. 1998 was preceded by 1997 El Nino. So in observations, you see increased rainfall here, decreased rainfall in the subtropical Western Pacific. And the model prediction captures this excessive rainfall and deficit rainfall pretty well. And then in the low-level circulation, observation shows this anomalous anticyclonic circulation, right? Warm Indian Ocean anticyclonic circulation in the northwestern Pacific. It's well predicted with the global climate model if you initialize the model with proper observations. So, of course, numerical models have skills exactly because these models have incorporated the correct physical processes, right? So if you take away Indian Ocean, I bet you will not be able to predict those rainfall patterns and low-level circulation patterns. Okay, so that's a kind of a brief summary, right? So I started with this map. I said it's a big lack of phenomena, a lack of effort to study, right? It turns out there are big anomalies in the circle. It was due to the lack of studies or efforts. In fact, the surprise is the El Nino, post-El Nino effect, but the El Nino inference is rather indirect, right? So it's through by charging the Indian Ocean and then Indian Ocean would discharge in the summer following El Nino, when El Nino has dissipated almost completely. El Nino influence clearly it's indirect through mediated by the Indian Ocean conditions. Does that make sense? Yeah. Okay. Great. Yeah. So this is what the past 2 decades work have identified this enormous anticyclonic circulation, and on the northern flank of this anomalous circulation is enhanced Meiyu rainband that could cause excessive rainfall, flooding in the middle and the lower reach of the Yangtze River. Okay. Yeah. So far I've emphasized the post El Nino effect on Yangtze River rainfall. So just as we feel we understood climate system somehow, there was another major flooding event in the Yangtze River in the summer of 2020. So this is extraordinarily challenging, right? Because it's COVID period. And then this map is a little busy, right? This is Japanese islands here, and this is the eastern coast of China. Taiwan is here. And then the blue color represents excessive rainfall, and orange decreased rainfall. And not kind of I guess just the major point is excessive rain band is right over the yellow Yangtze River. So this blue line is Yangtze River. One to the north is yellow river. Right? So you see this rainfall anomaly, excessive rainfall over the Yangtze River region. So this is all familiar. So now you see this anomalous anticyclonic circulation, southwesterly flow carrying water vapor, dumped water vapor in excessive rainfall. So this is Wuhan, right, in summer. And then by some measure, this 2020 is unprecedented in terms of summer rainfall in the Yangtze River Basin. 1998 is here, 2016 is here, 2018 is here, right? 2009. I'm not sure if this one has El Nino. Maybe it is. Anyway, so all this seems to make sense now. You see excessive rainfall along Yangtze River, enormous anticyclonic circulation, and so on. Except there's a problem. The problem is, or maybe before I will talk about that problem a little bit later. But this is just to illustrate how big the flooding was. Right? So there, I guess by the Yangtze River, there was this Leshan giant Buddha statue, 71 meters tall. And usually, just judging from the human height, right? So I think water level to the foot of Buddha is something like 7-8 meters. This is during 2020 summer. This is how much the water level has risen. Yeah, so there was so this all looks familiar. Oh, this must be let's blame on El Nino, right? Except there was the equatorial Pacific condition in the preceding winter of early 2020. The Nino Eastern Equatorial Pacific sea surface temperature is positive. It's extremely weak marginal El Nino. Nothing compared to an 2015, or 1992. So it was, yeah, El Nino may have contributed a little bit, but definitely El Nino by itself is not sufficient to explain excessive rainfall along the Yangtze River. So I will skip the details here, but I will just say, the official forecasts didn't predict flooding. It's because they conservatively took the empirical forecast, right? So I guess if you're in charge in prediction, you want to be accurate, but you also want to be safe, right? So if you have a new tool, you probably don't want to use your new tool to predict a major disaster. You want to use the try and comfortable method. So the Japanese Meteorological Agency, China Meteorological Administration, they issued something close to normal conditions for the 2000 Meiyu rainfall. So it turns out, this is observation. The rainfall, within this anomalous anticyclonic situation, see decreased rainfall, and along Yangtze River, see excessive rainfall. So it turns out, in both agencies, they have been running global climate models of their own, and they also looked at forecasts from other agencies, like Europe, North America, right? So they noticed actually, the reason the official forecast failed is because El Nino was so moderate, marginal. So you don't expect such weak El Nino to have a major anomalous condition all summer. So that's why the official forecast went to bet on the empirical forecast, because that's most comfortable forecast people have always been using. But when they were when they were deciding what forecast to issue, they actually noticed the global climate model forecast. I don't know what happens to, yeah. So the forecast initialized on June 1st, 2020, looks very similar to the observations, right? Especially in terms of the Yangtze River, excessive rainfall, reduced rainfall to the south. And then even the forecast initialized on April 1, as of course the magnitude of anomalies much weaker and more kind of later forecast. But the overall anomaly patterns look not too bad. Yeah. So this is I think it's a milestone in a sense. We understand why the official forecasters want to use the empirical forecast, because now you see conflicting forecast from empirical global numerical climate model. Which one you would bet on, right? That's the choice. And I guess, I guess nobody wants to. Numerical models, people didn't take this seriously. But this marks the occasion that the numerical models actually made a correct forecast, whereas the empirical models did not. So this is also telling us something, right? A few things. One is this anomalous anticyclonic rainfall pattern can be triggered not only by El Nino, but also from other conditions. People have looked at in much more detail what drives this rainfall pattern during the summer of 2020. Turns out it's still the Indian Ocean conditions, but with different twists, which I'm not going to get into there. But it's enough to see, I have emphasized the post-El Nino effect on Yangtze River rainfall up to this point. It's because the past events seem to correlate very well with El Nino, right? But 2020 was the exception. It turns out that the climate data, reliable climate data, become available maybe roughly 1950 onwards, right? So El Nino has a typical interval of 4 to 5 years. So you got at most 20 also El Nino events, right? So you have limited, very limited realization of what nature can do. So up to this point, you blame everything on El Nino, but this is a wake-up call. Saying, it's Indian Ocean, but it's not really triggered by El Nino. So this is telling us climate data, of course, are real, but they are real, but they may not sample all the possibilities. At least within limited lengths of observations. Yeah, so this is what I'm getting at, right? So El Nino southern oscillation, atmospheric oscillation, sometimes we call it. And so El Nino is the major predictor of East Asia climate anomalies, but the observed El Nino cycle has at most 15, 20 El Nino events since 1950. That's about the same number of weather cycles in one single season. So you expect you will have some skills in predicting either this many of weather, after this many of weather cycles, this many of El Nino cycles. But your skills are rather limited by the available sample size. This is a lesson learned in 2020 summer event. So how we are going to go about forward, right? So one of course, the big take home is weather forecast, weather variations. Weather studies have always been a big data science, right? So you have so many weather cycles. Is climate variability also big data science? It seems to be both related to atmospheric conditions. But I would argue climate variability is not yet a big data science. It's because you are limited by how many El Ninos. No matter how finely you observe El Nino conditions, the number of El Nino events are very limited. So one approach is perhaps generate big data from numerical climate models. In this case, we have utilized a novel simulation method called tropical Pacific pacemaker simulation. So usually the climate models are run by inputting observed greenhouse gases, aerosols. But so by this point, you probably agree, tropical Pacific conditions are important enough to merit some realistic representation. So a way to represent tropical Pacific restoring the sea surface temperature in tropical Pacific conditions, at least in terms of global mean surface temperature. The blue is observation, the black is Pacific pacemaker simulation. I think it's fair to say the model follows up and down pretty well. 2023, 2024, both record years for global mean surface temperature. Our model capture this and even predict 2023, 24 record. This red indicates prediction, not simulation. So anyway, so the idea is by initialize the couple model from this so-called pacemaker experiment, you can have let's say if you integrate the model 20 times, then you can generate 20 times more data a year after your initialization. So you can do it 200 times or 2,000 times. That will generate big data for you to analyze. And I'm probably not going to talk about the details, but this is just an example. This anomalous anticyclonic circulation, extremely important for Yangtze River rainfall, right? The southwesterly flow converges water vapor called excessive rainfall on the Yangtze River. So we know like preceding El Nino conditions is an important predictor. There are other predictors. So with available observations, you can compare the observed anticyclonic circulation preceding El Nino conditions, maybe by introducing more predictors. By introducing more predictors, you improve the correlation 0.4 to 0.5, but the data, number of data on the plot is limited by historical observations. You cannot generate real data from nothing. But with model, you can generate. This is 20 times more. We integrate the model 20 times. Let the model run for a year or so, and you generate 20 times more data. And this is by doing the same single predictor and bi-predictor correlation. The correlation from a single predictor increased from 0.3 to 0.5. So I think this improvement is much more believable. Of course, believable in number, right? This is real data, and this is model generated. You can judge whether. Of course, the real data cannot be replaced by model data by any means. Just looking at data density, it seems to be pretty good in justifying by introducing additional predictor other than El Nino conditions. Okay, as promised, I'm showing my last slide as AI-generated picture. So this is so my hometown is here, right? So it's exactly on the Meiyu rain band. So when I was a kid, often went out to look at the clouds in the sky, right? So I have no idea, the drifting clouds saw was actually feeding rainfall, the rainstorms along the river basin, and also the southwesterly flow in this AI-generated picture seem to be from our study and from other studies by others too, seem to show this winds over my hometown is part of a big, large scale, right? Anomalous anticyclonic circulation. And this anomalous anticyclonic circulation is induced by faraway phenomena such as El Nino, Indian Ocean capacitor. So only I don't know how many, 50 years, maybe even longer. Later, I realized what I saw. I feel I understand a little bit better what I saw when I was a kid in my hometown. And as Steve Chu mentioned the other day, right? As scientists, we feel very happy. We whether we could manage to do something useful in society science. This might be a case for my own self-satisfaction. Yeah, so that was the results I present today. For my own journey, 20 years, realize what I saw in the ocean. So that part of the 20 years in between, what I spent those years by going back. The other smart people, different ideas, scientists, debate, compete, ideas. That is I think important part of the scientific method. Seek by itself, through debating and through try and error. That's probably best I can try. Yeah, because whether I like it or not, that's not important. Other people, they're going to.
So much for a nice talk. I really enjoy it, especially. I just have questions. Right? So number one, actually, first of all, just a disclaimer. I'm a super layman on this.
Yeah, I consider my talk.
Thank you. Yes. So I think the first question is more like, we noticed that there's climate change, these like waves and all those, right? So will these be factors that will also be included? How significant is that? That's the first question. The second question is more like data thing, right? So because definitely understand like why you want big data, right? Like neural network or something to use AI to predict better. But of course, model generated ones be trusted less than the experimental ones. So probably one way is that you can actually use weights or something, right? Place higher emphasis on the experimental data, right, compared to the model generated one, right? Yeah. Perhaps by doing something like this, you can optimize your statistics.
Yeah. For your second question, there are now the national weather system. Every major national weather system, we have one operational climate forecast. Yes, that's very similar to weather forecast. In other words, weather forecast every morning we have a reality. Unfortunately, El Nino happened 4 or 5 years. Right, so you have a reality check. Yeah, unfortunately. So we don't have the. So in other words, in our lifetime, we may event. That was. But I think by forecast, by operating forecast, we at least have some reality on the model. I why that's again.
This question is more like climate change in the
Oh,
human
yeah.
activities?
Yeah. So because warmer climate allow the atmosphere more water vapor, so the flooding events are almost certain. Yeah, just because water vapor natural. That's all. And there's another aspect. So in terms of Yangtze River excessive rain flooding. Now, by now, you probably know what I'm talking about. One is El Nino, one is induced by something else. So some research suggests El Nino-induced excessive rainfall variations are not going to be changed that much, but the other factor-induced excessive rainfall events may become more large, more prominent, more frequent, larger amplitudes. In other words, without a numerical model, you might become, predicting summer rainfall along the Yangtze River may become a more and more difficult, if not impossible, task to handle.
Thank you for your talk. Sorry. I was wondering what's the mechanism behind the creation of El Nino? Like, do we know why it's created and why is such frequency?
I think we roughly know on a broad level, just because the El Nino basically it's not atmospheric phenomenon. It's not oceanographic phenomena. It's an ocean-atmosphere coupled phenomenon. It's only when you have an ocean atmosphere in contact with each other, you can generate El Nino. So El Nino, in fact, now can be routinely predicted 6 months or 9 months in advance. So that scale tells us we know something about El Nino.
And why is it 4 or 5 years?
Oh, that's because the El Nino, there's oscillatory mechanism. The oscillatory mechanism is in the ocean. The ocean has certain waves. 1 year is for those waves to go a complete round trip from along the equator and back to its starts. So that time scale sets the intervals of El Nino events, roughly. Yeah. Of course, there are chaotic components as well, stochastic.
Is it that? Yeah. Okay.
Okay, so we please come back in 2 minutes, and we will continue to our. Sorry, I just I think I just
we should have finished.
yeah, I think I just take a mistake. Sorry. So we could have
there was a question on the back. No, yeah. Maybe we can wrap up.
Thank you for your talk, professors. We know that the atmosphere ocean system is a chaotic system.
Yeah.
You just talked. And my question is, how can we determine that variation within the Enso cycle influence the subtropical high in a systematic rather than chaotic manner, and subsequently affect the position of the Jianghuai situation front? Furthermore, where does the boundary of the chaotic and regular you think?
Yeah, that's a good question. So in general, the tropical atmosphere is less chaotic. So in the tropics, once you know the ocean temperature, you can recreate the atmospheric conditions pretty well. So the degree of chaotic variability increases basically with latitude. In the tropics, it's less chaotic, but in mid latitudes, you have a strongest chaotic variability. The reason is because in the mid-latitude, there's a westerly flow in the upper troposphere, upper atmosphere. That's very intense, and that's the mechanism that generates storms that come and go during winter. So that the westerly jet is the source of chaotic variability. That's strongest in the latitudes. In other words, if you want to predict Indonesia rainfall, it's much easier. But if you want to predict like Yangtze River, the San Diego rainfall, that's much tougher. That's because it's closer to the westerly jet of the atmosphere, which generates chaotic variability.
Thank you.
Did you want to continue your question?
Yeah. Yeah, so those wave speed has to do with Earth's rotation. So Earth's rotation is fundamentally important. The large scale flow of the ocean and atmosphere that sets the speed and horizontal structures. That's why El Nino happens on the equator. Elsewhere, you cannot have El Nino because on the equator, the Earth's rotation effect is the weakest.
Okay, let's thanks, Professor Xiang. Okay, the third talk will begin at